So this week we're talking about sections 8.2 and 8.3. This is a continuation of the hypothesis testing stuff, but this time we're going to get a little more technical. So we are going to start talking about how to perform a hypothesis test given some simple assumptions. So in 8.2 and 8.3, what we're trying to do is test a population mean. So we have the mean of some variable, and we want to know whether it is equal to some given value or whether it disagrees with that value. And that's where our hypotheses come in. So what I've decided to do in this video is I'm going to make up an example and we'll go through it sort of organically. So I'll bring up all of the steps as we get to them. But there is this nice procedure which is given to us here. This is the page right after where we left off last time. And remember, at the end of our last lecture, we talked through all of these different terms, all of the definitions, but we didn't really see how to technically apply them. So if you'd like, you can go back and read over the definitions that we saw last time. I'm going to bring up those definitions as we come to them. But notice that here at the start of section 8.2, there's this nice procedure. It's a 6-step procedure that you can go through to solve all of these problems. So the good news is that this procedure is going to work on all of the problems that are going to come up in this section. The downside is just that it's kind of a complicated procedure to follow. So we're going to go through several examples involving this procedure, but in order to be able to apply these in section 8.2, it's important, sorry about that. In section 8.2, it's important that the population standard deviation is known. So this is 8.2's thing. In 8.3, we'll talk about what to do when you don't know the population standard deviation. So aside from that, we need two other assumptions, which is that we're taking some simple random sample in order to measure, or I should say approximate, this population mean. And we also need this variable that we're trying to measure to be normally distributed, or we need to be taking a large sample size. The reasons for this is that we want x bar to be normal. So the techniques that we're going to talk about are only applicable whenever x bar, our sample mean, is normally distributed. And to make that happen, we just need to have either a normal population variable or a large sample that we're taking. Okay, so if you'd like, you can look through these different steps. I'm going to bring them up as we come to them one by one, but I'm not going to keep referring back to this table. However, as you go through the problems in your homework, you can just have this table in front of you, and you can go step by step through these problems. So let's look at an example that I'm just going to make up. So here, a teacher is claiming that the test averages were normally distributed with a mean of 75 points and a standard deviation of 12 points. But you think that the average was significantly higher. So you've talked to your friends and they seem to all be getting really good scores, so you don't actually believe this teacher's claim. So I'm just going to go through the procedure that was outlined on that last page. So first, we're going to state our hypotheses. So here, the null hypothesis is always given by some equality. So the null hypothesis is just going to be the boring one that the teacher's telling the truth. So we're going to just say that the actual population mean is equal to 75. But you're putting forth an alternative hypothesis. If you think that the average is significantly higher, then the alternative hypothesis would be that mu is actually greater than 75. So this is going to just be a one-tailed hypothesis test. We'll see some examples later of two-tailed hypothesis testing, but the strategy is still essentially the same. So next, what you need to do is decide on a level of significance. And loosely speaking, you can think of this as being like the probability that you get it wrong by accident or by chance. So because this is just a probabilistic sample, like we're just sampling some random subgroup of our class and computing that sample mean, there's always a chance that we accidentally sample a bunch of people that did really well, or we accidentally sample a bunch of people that did poorly, and that will skew our results. So here in the level of significance, we're just trying to control for this. This is usually denoted alpha, and it's usually going to be 10% or 5% or 1%. And these are measuring the probabilities that you get an extreme result and deny the null hypothesis, even though it happens to be true. So you can think of these as the probabilities that we accidentally get an extreme result, even though the null hypothesis was true. So let me give you sort of a picture of what's going on here. So maybe let's fix an experimental design. So here's how we're going to actually test this hypothesis. We're going to sample some number of students, let's just say 9 random students. And then we'll compute the mean of their scores. So we'll compute X bar, just the average of those 9 students. We can't sample everybody, but we can sample 9 random students. And then we want to compare this X bar value to the claimed mean. So the teacher claims that the average should be 75. We would expect X bar to also be close to 75 if the teacher's telling the truth. Okay, so here's sort of the picture that we're going to be going with. So the teacher has claimed that the mean is 75. We also know that whenever you select some number of random students and compute X bar, we know that the distribution of X bar is going to be normal. So the picture that I've drawn is the distribution for X bar that we would expect. And we also know that the standard deviation for the sample mean is given by sigma divided by the square root of n. Now, in this case, the standard deviation for the population was 12, and then we're dividing by the square root of 9 because our sample size is 9. So if you'd like, I can scroll up real quick. We saw that the mean that the teacher claimed was 75, and the standard deviation that the teacher claimed was 12. So that means that for the sample mean, the standard deviation is going to be sigma over the square root of n, which ends up being 12 over 3, which is 4. So this standard deviation would just be 4. So this is the picture that we're looking at. And now let's say that we go out and we sample these 9 people and we compute X bar. So I'm going to draw X bar in green. There are a few different results that we might get. So I could go out and sample these 9 people, and maybe we come back with an average that lives over here. It's pretty close to mu. In this case, I wouldn't be very confident in rejecting this null hypothesis. So here, because our sample mean is so close to the teacher's stated mean, I would not reject the null hypothesis. So maybe this X bar ends up being something like 74 points or whatever. These are so close together that I might just trust the teacher. So we need to decide what the cutoff should be, where we stop trusting the teacher and we start to think that maybe he was lying. So let's say that we end up, rather than getting an X bar that lives close to the mean, let's say that we get an X bar value that's way over here. If we end up getting an extreme X bar value, then what we can notice is that if the teacher was telling the truth, there's not a very much likelihood that we get such an extreme X bar value that lives over here, because we know that most X bar values are supposed to fall within this middle region here. So if we get a very extreme X bar value, then we might be willing to reject the null hypothesis. So that's what we're looking for. We want to see if the sample mean ends up giving us an extreme value over here to the right. In this case, we're focused exclusively on this right tail because our alternative hypothesis was that mu is actually significantly bigger than 75. So we're looking over here at this tail. Okay, so let's talk about different ways of deciding whether your X bar value is extreme enough. So just for example, let's say that we went out and we surveyed 9 people and we got an X-bar value of 85. So our X-bar value lives somewhere over here. Now what we need to do is we need to decide whether that's extreme enough for us to reject the null hypothesis and say that X-bar is actually bigger than the teacher claims, or maybe that's not quite big enough for us to reject the null hypothesis and we just stick with the null hypothesis. Technically, you're essentially either rejecting or not rejecting the null hypothesis. It's not that you're proving one of these hypotheses to be true or false, because we can't do that. This is just a probabilistic process. But what we can do is we can decide whether we're pretty confident in rejecting the null hypothesis or whether we're not confident enough to reject the null hypothesis. So first what we need to do is in step 3, we want to take this picture and we want to standardize. So remember, whenever you standardize, you're looking at formulas like this. You're going to take your X-bar value, you subtract the mean in order to center this at 0, and then you divide by the standard deviation of the picture that you're looking at. In this case, that would be sigma over the square root of n, because that's the standard deviation in this picture. So whenever we standardize, what's going to happen is we'll get a similar picture. This time we've recentered at 0. So this is just the standard normal distribution. And what we end up getting in this particular case is we have our X-bar value was 85. We subtract the mean, and then we divide by the standard deviation, which we found to be 4. So this would be 10 over 4, which is 2.5. So whenever we standardize, the corresponding z-value that we get over here is a z-value of 2.5. So now we need to decide if that's an extreme enough z-value for us to reject or accept the null hypothesis. So here's how we do that. In step 4, there are actually 2 options. So maybe let me come back to the notes over here. What we've done so far is these first 3 steps. So we chose our hypotheses, we decided on the significance level. So actually I gave you a few options for the significance level. Let's just choose 10% as our significance level. And then we just finished computing the test statistic, which is just this z-value. So next we're going to have 2 different approaches. These are equivalent, so they'll come up with the same answer at the end. The answer being whether or not to reject the null hypothesis. So there's this critical value approach where you compare z-values, and there's the p-value approach where we compare areas. So I'll talk through both of those. So let's go back to the notes over here. So let's choose as our level of significance just 10%. So what that means is we want to get a z-value such that we would only get that z-value by chance 10% of the time if the teacher was telling the truth. So in other words, there's only a 10% chance that we're going to get such an extreme z-value if the teacher really is telling the truth. And if that's the case, then we can be pretty comfortable in rejecting the teacher's hypothesis. So what that means in terms of the picture is this. What you would do is you would find an area over here corresponding to 10% of the area. So that would be an alpha of 0.1. And that 10% of the area is going to correspond to the 10% of the most extreme values, or I should say maybe the top 10% most extreme values that you could get by chance, assuming that the teacher's distribution was correct. So if we end up getting a z-value that falls over here, this is called the critical region, then we would reject the null hypothesis, because we've gotten a z-value that's so extremely far to the right that there's only a 10% chance that we would get this sort of z-value if the teacher was telling the truth. Therefore, we disbelieve the teacher. Now, if instead we were getting a z-value that lived somewhere pretty close to the mean, then we wouldn't be comfortable rejecting the null hypothesis, because there's a pretty good chance that we end up getting z-values that live close to the mean. But because our z-value is so far away from the mean, it's starting to look like we're going to reject the null hypothesis here. But we need to decide exactly how to do that. And one way is by talking about the critical values. So the critical value approach is this. So we know that our z-value is 2.5. The critical value is going to be this value here, the one that's represented by this vertical bar. So that this will be the critical value. And what we'll say is that if our z-value is bigger than the critical value, in other words, it's more extreme than the critical value, then we will reject the null hypothesis, because what we're getting is a z-value that's way to the right relative to where the teacher said we should be. So we would reject the null hypothesis in this case. If the z-value that we got from the test statistic was over here to the left of the critical value, then we would not reject the null hypothesis. And let's think about how we should come up with that critical value. The critical value is supposed to be the z-value that has 10% of the area to the right of it. So this is usually written as z sub alpha. In this case, that would be z sub 0.1. And remember that subscript is the area to the right of this z-value. So if I want an area of 10% to the right of my z-value, then I can use the table to figure out what this z-value should be. So remember, I want an area of 10% to the right, which means I want an area of 90% to the left. So I would look at the areas in this table, and I would try to find the area of 90% to the left. Now it looks like there are a few close options. So there's a 0.8997, and there's a 0.9015. Those are the closest that you can get to having 90% as your left area. This one's technically a little bit closer. So 0.8997, that's only 0.0003 away from what we want. So that's the closest one. And it has a corresponding z-value of, it looks like 1.28. So that's in the 1.2 row and the 0.08 column. So our z-value would be 1.28. And that is our critical value. So in this case, we would get a critical value of 1.28. And in this step, what we would do is once we know that our critical value is 1.28, we also know that our test statistic is 2.5. Because our test statistic is more extreme than our critical value, we would move on to step 5, and we would say that we should reject the teacher's null hypothesis, because our test statistic is more extreme than the cutoff that we were willing to put up with. So in other words, if we ended up getting a z-value that lived over here that was less than 1.28, then we would be pretty close to what the teacher said we should be at. But because we ended up getting a test statistic that's significantly further over to the right, it's past our critical value, we are willing to reject the null hypothesis. So that's one way of deciding to reject the null hypothesis. There's a similar way that you might take here, and again, these are equivalent, so you can sort of just decide which one you want to do. But this one is called using the p-value. And the idea behind that one is this. Rather than comparing these two z's, so we compared the critical value, which was a z-value, to the z-value that we got from the test statistic, there's another equivalent way of thinking about this, which is to compare the areas that you're looking at. So notice that the yellow area is 10%. What we could do is we could compute the area to the right of the test statistic. That would be the green area here. And that sort of tells you what the likelihood is of getting a test statistic as extreme as yours or more extreme than that. So notice this is the area that lives to the right of your test statistic. And therefore, this is describing the probability, if the teacher was telling the truth, of getting a z-value as extreme or more extreme than the z-value that you actually got. So what we do in this case is we would just compute the area that I've just shaded. So we would compute that area to the right of the z-value 2.5. And again, in order to do this, we'll use the table. So we're looking at a z-value of 2.5. So I would come up here. Here's my z-value of 2.5. And it has a corresponding left area of 0.9938. That would be your left area over here. So this is 0.9938. And that means that the area to the right, which is what we're trying to compute, would be 0.0062. So if I come back over to my notes here, then what I would get is an area to the right. Well, so actually, whenever we say the p-value, that area to the right is going to be called p. It's the area that lives at your z-value or more extreme than your z-value. So in this case, our z-value was a 2.5, and if we look there or more extreme than that, then we would be looking at this green shaded area. And what we just saw is that that green shaded area is 0.0062. And now what this can be interpreted as is you basically have a less than 1% chance of getting a z-value as extreme as the one that we did if the teacher is telling the truth. So if the teacher was telling the truth, it would be very unlikely that you would get a z-score of 2.5 or more. But that's what we got. So therefore, we're comfortable in rejecting the null hypothesis. So because we were willing to put up with an area of 10%, and we ended up getting an area of 0.0062, sorry, I should say, well, this is fine. I'll say 0.1. Because this area is so much smaller than alpha, or really just smaller than alpha at all, we would reject the null hypothesis in this case. So in the p-value method, you're comparing these areas, and we find that the p-value that we got was smaller than alpha, therefore we reject the null hypothesis. Over here, you're comparing the z-scores. But both of these are ways of measuring whether your test statistic is too extreme to seem consistent with the teacher's original distribution. So in both of these cases, whenever we make it to step 5, we would reject the null hypothesis. So both of these will reject the null hypothesis. They'll always get the same answer. You can just decide whether you would prefer to compare the z-scores or compare the areas. Okay, and then your last thing is to interpret your answer. And so what I would say as your interpretation is there's only a 0.62% chance that we'd get such an extreme test statistic if the teacher told the truth. So we reject H0, the null hypothesis. So in other words, what we've done is the teacher said the average was about 75. What we did is we sampled 9 people, and we got a significantly higher average just from that random group of 9 people. There's only a 0.62% chance that you would get from a random group of 9 people an average as high as the one that we got if the teacher was telling the truth. So therefore, we're going to reject the null hypothesis because there's a very low chance that we would get such an extreme result if the teacher were telling the truth. So That's a very broad overview of the procedure that we're going to be going through in 8.2 and 8.3. In the next video, we'll get into the actual examples in the notes. I don't expect you to be immediately comfortable with this whole procedure. I just wanted you to see sort of step by step what's going on with some drawings.